Cryovolcanism, a fascinating geological phenomenon, involves the eruption of volatiles such as water, ammonia, or methane, instead of molten rock, and is a key process on many of the icy moons in our solar system. These icy moons, orbiting the giant planets, harbor subsurface oceans beneath their frozen exteriors, making them intriguing subjects for the study of cryovolcanism. The science of cryovolcanism on these celestial bodies sheds light on their geological activity, internal composition, and the potential for harboring life. At the heart of cryovolcanism is the presence of subsurface oceans, kept liquid by a combination of factors including tidal heating and radioactive decay. Tidal heating, in particular, plays a significant role, especially for moons in close proximity to their parent planets, such as Europa around Jupiter and Enceladus around Saturn. The gravitational pull from these massive planets and their other moons generates significant tidal forces, causing the icy moons to flex and produce heat through frictional processes within their interiors. This heat prevents the subsurface oceans from freezing solid, creating the conditions necessary for cryovolcanism. Cryovolcanoes, or ice volcanoes, on these moons, erupt with a mixture of substances that can include water, ammonia, methane, and carbon dioxide, depending on the moon's composition. These eruptions are driven by the internal heat of the moon, causing the subsurface volatile materials to expand and find their way through the moon's icy crust, erupting as plumes or forming icy deposits on the surface. Unlike traditional volcanism on Earth, which is characterized by hot, molten lava, cryovolcanism involves the movement and eruption of substances in a semi-liquid or gaseous state due to the extremely low temperatures. One of the most compelling examples of cryovolcanism is observed on Enceladus, one of Saturn's moons. Enceladus is known for its active geysers, spewing jets of water vapor and ice particles from cracks in the moon's icy surface, particularly from a region known as the Tiger Stripes near its south pole. These eruptions are so powerful that they contribute material to one of Saturn's rings, the E ring. The process is driven by the internal heat of Enceladus, which keeps the water beneath its icy shell in a liquid state, allowing it to escape through the cracks and fissures in the crust. Europa, orbiting Jupiter, is another prime candidate for cryovolcanism, though its activity may be less obvious than that of Enceladus. Europa's surface is crisscrossed with lines and cracks, suggesting a dynamic and active crust. While direct evidence of active cryovolcanism on Europa is more elusive, models and indirect observations suggest that it too has a subsurface ocean that could be driving similar processes. The Hubble Space Telescope has detected what appear to be plumes of water vapor erupting from Europa's surface, hinting at cryovolcanic activity. The study of cryovolcanism is not only about understanding these icy eruptions themselves but also about what they can tell us about the internal composition and dynamics of these moons. The materials ejected in cryovolcanic eruptions provide clues about the subsurface ocean's composition and, by extension, the potential for supporting life. For instance, the detection of organic compounds in the plumes of Enceladus raises exciting possibilities about the moon's habitability. Cryovolcanism also plays a significant role in shaping the surfaces of these moons. The deposition of materials from cryovolcanic eruptions can lead to the formation of new surface features, including plains, ridges, and mountains made of water ice and other volatiles. This continuous resurfacing can erase impact craters and other marks of aging, giving these moons a younger appearance and altering their reflectivity and thermal properties. The exploration of cryovolcanism on icy moons is an ongoing field of study, with future missions planned to delve deeper into these phenomena. The Europa Clipper mission, for example, aims to conduct detailed reconnaissance of Europa's surface, subsurface, and potential plumes, providing new insights into its cryovolcanic activity and habitability. Similarly, continued observations and analysis of Enceladus and other icy moons will further our understanding of cryovolcanism and its implications for astrobiology and planetary science. In conclusion, the science of cryovolcanism on icy moons presents a window into the dynamic processes that govern these distant worlds. Through the study of these icy eruptions, scientists can gain insights into the internal structures, compositions, and potentially habitable environments of the moons orbiting the gas giants in our solar system. As our exploration of these celestial bodies continues, so too will our understanding of the fascinating phenomenon of cryovolcanism and its role in the broader context of planetary science and astrobiology.